The exciting thing about the second flyby from a magnetic field standpoint at Mercury is that we were able to obtain measurements for the very first time from the western hemisphere of the planet. The graphic that you're looking at shows the paths from which we have magnetometer data suitable for understanding the intrinsic field of the planet. And you'll notice that the second flyby of MESSENGER is the only one that provides data for east longitudes greater than 180 degrees, that is in the western hemisphere. So in the next graphic I show the magnetic fields that were observed, the magnitude of the magnetic fields observed on MESSENGER's first and second flyby. And what you notice is that the maximum magnetic field, and that's a measure of the intensity of the planetary magnetic field, those maxima were almost identical between the first and the second flyby. They agreed to within almost 2%. That's very significant because even though they were on opposite hemispheres of the planet, they observed almost exactly the same magnitude field. That means that the planetary's magnetic moment is very much centered on the planet's rotation axis, and it also means that the orientation of the planet's magnetic moment is very tightly aligned with the rotation axis of the planet to within about 2 degrees. For comparison, Earth's magnetic field is tilted by 11 degrees relative to the rotation axis. Well, even though the magnetic fields were similar, there was a significant difference between the first flyby and the second one, and I illustrate that in the second graphic. The second graphic shows the angle between the magnetic field and north observed for the first flyby and the second flyby as the spacecraft was outbound from the region controlled by Mercury's magnetic field, the magnetosphere, back into the solar wind. And at that crossing, you notice in the first flyby, the magnetic field remained northward, indicating that that was the direction of the solar wind magnetic field at that time. For the second flyby, the magnetic field turned strongly southward as we crossed that magnetopause boundary and remained southward, indicating that we had a southward solar wind magnetic field at the time of the second flyby. The reason that's so important is illustrated on the next graphic, which shows the magnetic lines of force that we would expect to find as they would be configured in the dawn-dusk meridian plane as viewed from the sun. For a southward solar wind field, you notice that the solar wind field is directly connected with the planet's magnetic field and actually provides direct access to the surface of the planet over large regions of the north and the southern polar regions of the planet. For a northward solar wind magnetic field, there's very little interaction between the planetary magnetic field and the solar wind, so there's much less access of material from the solar wind to the surface of the planet. During the second flyby, we saw numerous examples of strong interaction and strong dynamics between the solar wind and Mercury's magnetic field. And I want to show you one of those in the animation. In this animation, I'll be zooming in on the outbound crossing of the magnetopause. You can see the dots there are showing the time for which we're showing the heading there in the lower right. And there it's crossing the magnetopause where the field is turning from north to south. And at the same time it crossed the magnetopause, there was a very strong pointing of the magnetic field towards the planet, which was very surprising. You'll see this run again. Pay attention to that. As we're coming up to the magnetopause, the field is northward, and you'll see it start to turn south. There it goes south, and there it's pointing actually toward the planet, very strongly towards the planet. At all magnetopause crossings we've observed at other planets, we've never seen a magnetic field pointed anywhere near that strongly across the magnetopause. And that indicates that the energy transfer during this encounter was perhaps 100 times greater in intensity than it is at the Earth, meaning that the total energy transfer into Mercury's magnetic field region was perhaps the equivalent of, say, 100 medium-sized power plants. And that energy is channeled along the magnetic lines of force to the surface of the planet, where it has a number of consequences, and one of which is populating the neutral tenuous atmosphere around the planet.
The primary instrument on MESSENGER for studying the exosphere is the Mercury Atmospheric and Surface Composition Spectrometer, or MASS for short. And the way MASS works is it basically scans through the ultraviolet and visible portion of the wavelength spectrum, and it searches for emissions from the atoms and molecules that make up the exosphere. The colored portions under the histograms are essentially the emission intensity at a particular wavelength. And because atoms of a given species only emit light at a certain wavelength, or certain wavelengths, depending on the species, these are a unique fingerprint of the atoms that are doing the emitting. And for sodium, this occurs in the yellow portion of the visible spectrum, and for calcium, the wavelength is in the blue part of the visible spectrum. And now, both sodium and calcium have been observed from Earth using the ground-based telescopes. But during the second flyby, we got the first ever simultaneous observations of both sodium and calcium, and in a minute I'll tell you why that's so important. If I can have the next slide, please. This shows you similar observations that we made of magnesium emission in the exosphere. And magnesium has its wavelength of emission in the ultraviolet. Because the Earth's atmosphere is basically opaque in the sense that it blocks or absorbs the UV radiation that's coming in from outer space, you cannot observe this particular emission from ground-based telescopes. So the mask observations that we obtained this time are the first ever detection of magnesium in the exosphere of Mercury. And that's important because for a long time it's been expected that magnesium was a component of the surface of material of Mercury. The atoms that we see in the exosphere primarily originate from the surface. They're released in various processes. And so the fact that we observe it in the exosphere means that magnesium is definitely a part of the Mercury surface. And that is one of the important reasons for studying the exosphere, is that it provides unique information on the surface material. Now, I'm going to show you some observations of extended tail emission that we made during the second flyby. And to set that up, I'm going to ask that we run a little animation. So what you're seeing here is the sun is on the left, and north is up, and the spacecraft is moving towards the planet from the right to the left. And as it's doing so, it's rotating about the Sun-Mercury line up and down, and basically doing sort of a push broom sweeping across the tail. So it's mapping out the spatial distribution of the sodium emissions. Now, each of these little boxes that you're seeing is an individual sodium observation. The color scale goes from dark to bright, where bright is relatively more emission. And once we have them all, we interpolate to fill in the gaps like you just saw, and we produce these images of the sodium emission in the tail. Now, if we can go to the next slide, talk about this actual image. The small-scale structure that you see possibly has some of the viewing geometry still mixed in. So it's more important to focus on the broad-scale features that you see here. And what we have are two extended regions of emission that are located in the north and the south at the higher latitudes. And what this says is that the processes that are releasing these sodium atoms from the surface and getting them out into the exosphere have to have some element of them that is leading to this high latitude enhancement. And if we go to the next image, this is the corresponding image of the calcium observations in the tail region. And what you can see is that its distribution is different. As opposed to the sodium, which was peaked in the north and the south, very little in the equator, the calcium emission is symmetric with its peak at the equatorial region. And so what you see here is the power of these simultaneous observations, because until now we didn't have any idea of what the detailed spatial distribution in the tail region was of the sodium and the calcium at the same time. And this is going to tell us what's going on, because the differences in these distributions is related to the processes that are releasing the atoms from the surface, and therefore gives us an indication of the relative importance of these various processes. And one point I want to make here is that until now, people have always referred to the sodium tail of Mercury because it's been the thing most observed from Earth. But what we're seeing here is that Mercury simply has a tail. We see calcium emission in the tail, we see sodium emission, and we also have seen magnesium, although I'm not showing an image of that today. If I can go to the next slide, what this shows you is a comparison of the sodium tail emission in both the first and second flybys. And what you can see is that although they both have this high latitude enhancement in the emission, in the first flyby it was more asymmetric, and the north was brighter than what you saw in the south. Whereas in the second flyby, the sodium emission is more not uniform, but more overall symmetric in both the north and the south. And the temporal changes like this are important to understand too, because these are the things that we can tie into what's happening in the rest of the system. For example, Brian talked about the magnetosphere being much more active during the second flyby, having a lot of plasma from the solar wind deposited in both the north and the south hemispheres, and maybe that's what's going on here as far as the sodium emission, in that it's more symmetric in both the north and the south this time around. Now, these images I've shown you are simply a snapshot in time of a very rapidly changing system. And when we get into orbit, we're going to be mapping these distributions daily. And so we'll be able to get a much greater handle on the spatial and temporal variations that are going on. And when we combine those with the other observations from the other instruments, we'll be able to put the whole puzzle together and understand this complex interaction that's going on between the surface, the exosphere, and the magnetosphere.